on, this is lecture 4 of Lean for Scientists and Engineers. Welcome, everyone. We have the overall goal of this is to introduce scientists and engineers to logic and proofs and teach how to write these in Lean and how to do functional programming in Lean 4.2. So we can write programs that we can execute in Lean and then connect these together so we can have provably correct programs for scientific computing. And we are now on lecture 4, Proofs with Structure 2. We have been so far closely following the Mechanics of Proof textbook by Heather Macbeth, which introduces Lean to people with like a sophomore level background in mathematics. And next week, we're going to be getting into functions and types and moving into calculus-based proofs before we'll be taking a week off while I travel. For everyone in person, come in person next week, but I'm actually going to be in New York, so I will be joining online, and I won't see you, but good to see you today. So I need to reorganize this. Excuse me. The schedule is to move exists and for all to the backside. There. Okay. We will be recapping lecture 3 briefly and then moving into some of the additional logical terms that we didn't cover last time, and showing some Lean proofs about exists and for all. So one of the things we talked about last time is that I do want to hit on a second time to reinforce this is when you're defining some kind of problem, should you use have, or you should be adding a hypothesis. So on the front side, we have two hypotheses, a minus 5 times b is equal to 4, and another that's b plus 2 is equal to 3, and these will be leading to implying a is equal to 9. And this can be proved by first coming up with b is equal to 1 using have and h2, and then we go and we prove the final goal. This is the right way to do it, essentially. If you look at this and you say, well, I know that b is equal to 1, let me just add this into my premises, add this into my assumptions about the situation, that is problematic for these reasons. We've changed the theorem statement, so it's no longer the same theorem statement as it was before, and we don't actually know if this new premise, HB, if that's true, since we haven't actually provided the justification for it. So that's risky, because if HB contradicts any other hypothesis, then we're really in trouble. And the reason for that is the principle of logical explosion, which is why we cannot start up a theorem statement with a set of premises that has a contradiction in it. We can't. This leads to the principle of explosion, which we talked about more. You can revisit the Wikipedia page for that, but you can prove anything. And we don't want to be able to prove anything. We can prove false things, incorrect things if we do that, and that's not actually helpful. Lean has some tools to do some kinds of searching for counterexamples, which is a useful way to detect if you have any contradictions. It doesn't always work, but it can be handy if you are crafting your own set of premises and you want them to reflect some kind of thing, and you want to just be careful that you don't actually introduce any contradictions without realizing it. We also showed an example last time where it's possible to set up your theorem statement in a way that you think it's right, but it's not completely right either, and then it doesn't lead to where you intended it to do. That was the skydiver example. Okay, I'm also putting these again because these are some of the hardest things to get comfortable with when you're learning lean. So how do you find a tactic? You have a goal in your proof. You don't know how to prove it. You'd love for a magical tactic to just sort of solve your problem, and you can't just do that. Tactics aren't magic. They apply these mechanistic rules to solve your problem and close your goals. You need to find the ones that are appropriate for the goal that you're looking at, and you can find lists of different tactics along with glossaries on how to use those. And if you have a proof in hand and you want to see what a tactic is doing, you can get the documentation and examples by putting your mouse over in VS Code. And there's also the challenge of finding theorems. So we introduced how do you apply known theorems to your proofs? If something is in the library of proofs, MathLib, and you want to be able to access that, you can search for it. You can also use Moogle, which helps you to use natural language to search for these things. And again, if you can find, so Cullen Jones, who's a member of my lab, has spent a lot of time solving the kinds of algebraic and calculus-based proofs that are interesting to scientists and engineers. He has sort of pulled out the ones that he finds he's using often. There are also tactics. We mentioned the ASUP tactic. We didn't use that in any examples, but ASUP is one way you can it will try a bunch of things to prove it, and then if it finds certain theorems in MATLAB are useful, it will tell you which ones it found. And again, you can use mouse over in VS Code to get documentation and examples. All right, then give me a minute. I don't have the chat open yet, so if people are asking questions, I'm not seeing them. Okay, now I got chat up. All right. Yes, and welcome to the online meeting, Colin. There's, yep, I'll leave it at that. Okay, so the other thing we started talking about, we're going to finish up this slide basically, is this set of logical symbols. If you're new to logic, then you haven't seen these before. This is a little bit of alphabet for you to learn, but this is the shorthand way to describe and, or, not, implies, if and only if, which is just, I mean, it's very intuitive. It implies in both directions. And then we have exists and for all. So today we're basically going to wrap up this slide and we're going to talk about the rest of these. Last time we talked about and. So here's an example of and. If our first proposition is molecule is aromatic and a second proposition is molecule is alcohol, then and links these together. We have a molecule like phenol, which is aromatic and an alcohol. And P being true, Q being true, then the joint statement of both of these is true. Or it could be about pollutants, for example. We could have, maybe you have a beaker or a sample or some environmental situation, and if it contains acrolein or it contains hydrogen cyanide, then it is acutely toxic. And in this case, you don't need both of these present, you only need one of them. So we talked about these truth tables, that P being true, Q being true, implies P or Q is true. If one of these is false, the or statement is still true altogether, but the or statement is false if both of them are false. We also did some proofs in Lean, where we essentially, if you have an and proof, that makes your proof harder because you need to go and prove P, and you're not finished yet proving the joint statement. You need to finish and write a second proof to prove Q, and now you've proven both, so you're good to go. In contrast, a proof about or, you can pick one, basically. Like if you can prove it with the left side of the or, you can close the goal, or you can prove it with the right side of the goal. And that's our review of lecture 3. So on to not. Not is really simple. This one's different. It applies to only one term at a time. If P is true, then not P is false. And if P is false, then not P is true. So the truth table just looks like this. It's pretty simple, and I will just leave it like that. I will mention not will take order of operations precedence over other things. So if you have and, or, and things like that, and not is mixed in with those, you resolve the not first before you move on to do the other things. Okay. Implies. So implies, you can read this as if P, then Q. So my little example is if I'm detecting argon and Q is detecting a noble gas, my joint statement would be read as detecting argon implies detecting a noble gas. Or if I'm detecting argon, then I'm detecting a noble gas. And the truth table comes out this way, where let me just jump in with the colored version as well. P being true and Q being true makes the joint statement P implies Q true. P being true and Q being false makes the joint statement P implies Q false. Okay? Think about that. Just give you a minute. Okay, so because P is true, and I'm going out there and I'm noticing that, I'm not seeing Q being true. That means my if-then statement is not true. I don't believe my if-then statement. I don't believe the implication statement. So the implication statement is false because this is not holding. But in the other cases, I do believe the implication statement. That's kind of how this works. If the chemistry example is making you a little bit confused, I structured this as a simpler way to deal with this, but part of this is I can have, let's pick a different noble gas. Let's do neon, for example. I could be false. I'm not detecting argon, but I am detecting a noble gas. That doesn't invalidate this P implies Q. I could be detecting a noble gas, but I'm detecting something like neon. So that's a situation where you'd be looking at this second example. This third example, well, I can believe that detecting argon leads to detecting a noble gas. I'm just not detecting argon right now. I'm not detecting a noble gas either. Okay, maybe I'm detecting hydrogen. Hydrogen is not a noble gas, nor is it argon. Okay, then P implies Q still holds. So this is the overall truth table. Like I mentioned last time, the theorem provers, logical systems, they'll often define what implication means by way of the truth table. So it's like, this is the scenario, because if you define implication and you don't have a way for it to resolve false, false, then this is sort of incomplete and you won't end up with some kind of useful rule system. So often this is the ground level definition of what implies is. Okay. So I have some more comments about implication in general, because this one's an interesting one, and an or are pretty straightforward and cut and dry. We've been writing lots of proofs in Lean, and the idea of implication is in every single one of these. When we have hypotheses, in front implies the end. So this is from lecture 1. We would have an airplane traveling. Remember, there was 450 miles that it flew, and it flew 3 hours in one direction and 5 hours in the other direction. It was with the wind, then against the wind, and so forth. So prove that the speed of the plane was 120 miles per hour. That was a little thing that we solved. Okay. This involves implication. The premises imply the conclusion. The assumptions imply the conjecture. The hypotheses imply, that's what is in a lean example or a lean theorem statement. This colon stands in for that. And so implication is fundamental. We're not using the right pointing arrow here because that's reserved for other things in lean. When you use the right arrow in lean, it does involve the implication operator. It's also used in defining functions. Okay, and functions we're going to end up doing a real deep dive into next week, next class. But today we're just talking about the logic and getting into that. But again, thinking of it as the if P then Q, if these premises hold, then Q, then the stuff on the other side. If I state the theorem, I haven't proven that it indeed follows, but then that's what the proof which follows does, okay? The other curious thing is that P implies Q is not fundamental. I can actually use the three previous cases. I can use and, I can use or, and I can use not. And if I'm just using not P or Q, I can actually construct the same truth table as I get from implies. If I would have not P or Q, I would end up with, let me jump back over to the or case. Not P would switch the truth values of P in all of these cases. It would keep, because Q is true, these would still be true, but it would switch the truth value of the latter column, and it will end up matching the P implies Q column. So that's what I mean by P implies Q can be rewritten as not P or Q. And it's less intuitive for humans. Like we generally think in terms of if and then, or something causes something else to be true. We don't think not P or Q, that's weird. But it's actually very useful for automated theorem provers that can very efficiently crunch through and, or, and not statements. And they'll often use that kind of this logical result to do, it's called resolution in automated theorem proving. You don't need to worry about that stuff. It's sort of all stuff that kind of happens under the hood of lean or other kinds of theorem provers as they're employing different tactics to figure out how to resolve statements. But that is another useful point to make. And you can prove this in lean. You could say, I'm going to define not P or Q, and I can define P implies Q, and I could prove that there's an if and only if relationship between these two. And Mechanics of Proof Chapter 5, you could read those sections, learn about those tactics and things, and do that proof yourself, which is fun and satisfying. Another point that I want to bring up is causality in science. So I brought this book as a prop. Okay. My video virtual background is blocking it out. Let's turn that off. Okay. This is The Book of Why by Judea Pearl. It's written for a general audience about the new science of cause and effect. So there's this whole research area in the realm of automated reasoning, and here, let me get my normal background back on. Some people, and there's whole sets of computer programs to think about causality. that's a realm of automated reasoning. I'm not an expert in that myself. I've been focusing more on the theorem proving side of things, on the scientific computing side of things, but people, especially in the biomedical fields, medicine is very concerned with causation. Smoking causes lung cancer. Lung cancer does not cause smoking. So this is not an equality relationship. It doesn't go both ways. There's also a difference between causation and correlation. Okay, we also see a correlation between smoking and lung cancer. Okay, these are correlated, but they're not. Lung cancer does not cause smoking. The causation works in the other direction. There are other kinds of causal relationships. Like I could say, two things are correlated with each other, but they don't cause each other. Neither one causes the other. There's a third thing that causes both of them. Okay, like that's another kind of area. And there's some work in bringing the computational tools people use to analyze causation in science and bring those into formal logical reasoning tools. Lean has the capability, and if this is your cup of tea, then I'd encourage you to dig in and start exploring ways to do that in Lean and potentially connect it to the other rich programming things that Lean offers. And yeah, implication, okay. When we're dealing with this too, there's also probabilistic logic because I've gone out and I've collected a bunch of data. So I have some people who had lung cancer and they never smoked. And I have some people who smoked and didn't get lung cancer. So there's uncertainty there in this implication symbol. And probabilistic reasoning is this whole other thing. Today we're only talking about the Boolean forms of reasoning where these only have fixed values of true or false. But wanted to just mention another point that there's a whole realm of reasoning machinery where people will do probabilistic reasoning where smoking is probabilistic and lung cancer is probabilistic. And this implication statement itself might also be probabilistic, where the truth value is between 0 and 1. Lean has the machinery it needs to do that, but it doesn't. But I think there's still gaps in the math library and so forth. But again, if that's something you're curious about, it's something one could explore with Lean because it is general purpose with its dependent type theory foundation. All right. 1 minute, my computer needs to be plugged in. Okay. So there's a lot more to say about implication this time. So the next one is if and only if. Sometimes this is called by implication, implication going both ways. You might, in common natural language, we would say if and only if. So first premise might be a molecule is a hydrocarbon and a molecule contains only carbon and hydrogen atoms. So we would then have the if and only if statement. A molecule is a hydrocarbon if and only if it contains only carbon and hydrogen atoms. And so I would be saying that being a hydrocarbon implies containing only carbon and hydrogen atoms, but it also goes in the reverse direction. Containing only carbon and hydrogen atoms implies being a hydrocarbon. This is the way the truth table looks. It's different from the one directional implication because now if here I'll jump back to the other one. So previously, if Q is true, that does not imply that can involve P being false. So Q being true doesn't require my P to be true. But in the if and only if case, that is switched because Q being true requires P to be true because the implication is stronger, it goes both directions. And I think, I was trying to think really hard about coming up with like chemistry or physics examples of this, and I kept coming up with basically definitions of things. Like if I define something in some way, then the definition is going to be described by the thing that it is, and the thing that it is going to imply the definition. There are a lot more examples to come up with where implication only goes in one direction, because in science we have so many exceptions that come up. In the context of some real world example, we have exceptions all over the place. And so we very often have implication going in one direction, but the exceptions are what prevent the implication from going in the backwards direction. The only time when we don't have any exceptions at all is kind of in the realm of defining things a certain way. Give me some more time and I might have some better examples or more interesting examples, but this is what I came up with for today. So we have all these truth tables, or and or not, implies, if and only if, and they can be combined to reason about compound statements. So consider not P and not, excuse me, I can have P and not Q, and I'm going to negate the whole compound statement. So here's an example of something. This is an example of mechanics of proof, where you just reason about these one by one. You follow order of operations. You start with the not on the inside, and so I'm going to switch the Q to not Q. Now I have all the sets of my truth values for not Q, and I'm going to apply the AND rule to do P and not Q. And so and, well, one of these is false, so P and not Q is false. Both of these are false, well, both will be false. Here, both of these are true, so I end up with one of them being true. And then I do a not on this, I change over every single one of these truth values, and now I have the truth, the set for not P and not Q. You can do these by hand to get a little bit more practice and get some more intuition about this if it ends up being relevant to what you're working on. Plenty of computational tools to very efficiently crunch through these. Some of the automated theorem provers are able to handle large databases with thousands of little statements. So you might imagine a library I wrote a proposal like, could we develop a library of thousands of little statements about molecules and their NMR spectra? Okay, like could we develop that and have a computer sort of evaluate these all on the fly in order to do reasoning about that kind of thing? And there are, algorithms for dealing with that. But in general, that doesn't, I bring all of this up. One more slide on this. So mechanics of proof, chapter 5, has this little passage. If you abstract away the numbers, definitions, equations, and inequalities, you are left with pure logic problems, okay? We only have propositions anymore. I don't even have an equality or an inequality. That is abstracted away into just a statement, okay? The pure logic tactics that we used apply, and we used constructor so far. Obtain is not one we're going to cover in this class, but you'll see me mention it later in this lecture. We can use these pure logic tactics in order to prove things. This is P or Q, and not P implies P. So we can prove that purely logical statement by applying purely logical tactics in lean, and we can close that goal and get a guarantee that this example is true. And Professor Macbeth says it's hardly worth trying to write proofs like this in words. Like, why would you? I mean, I spoke it out here, okay, But the P and Q are abstract propositions, and this is just a game of manipulation. And this is why we're not directly addressing chapter 5 in Lean, and I'm going to move on from this because most of the time in science and engineering, we have rich content in P and Q. This is an inequality that corresponds to some kind of science. This is some number that I actually, it's 7, and it matters that 7 is not 14. Okay. That's also connecting to the syntax versus semantics connection. This is pure syntax. And right, and I was going to bring up one more. There was another point, but I forgot. Okay. Oh, no, back to the... Yep. The purpose of where we're driving for this is we want to drive this to scientific computing. And we are, that was the point. Yep. We're driving this toward developing scientific computing software. And in general, that's going to push us in other directions. Okay, but if you're curious about that, definitely dig into chapter 5 of Mechanics of Proof. Crunch through those things, develop your skills with tactics. You do need those tactics if you're invoking those logical operators and you need to write proofs about them, and so on. Okay. Any questions about logic? I think we're good. So, okay. Moving on to definitions. So far, we've always used little self-contained examples or lemmas or theorems defined in Lean. And today we're going to have some definitions for the first time. So I'm going to say a few words about that. The reason is they allow us to reuse terms and objects outside of these individual examples and theorems. So we can facilitate modular code. Those of you who are in computer science, that's a big deal. It's important to make code modular. So it makes testing better. It makes reusability, extensibility, all those things are better when code is modular. For Lean, it also enables us to do verification of different parts of code. If I define a proposition and it's here, I can prove that proposition to be true, and now I can use it elsewhere. That's the basis of MATLAB. If I define functions, I can then use those functions to do scientific computing software, and then I can write proofs about those functions. If I just introduce a function inside of a little individual example, I can't use it outside of that. So this is what definitions are for. And we will see our first code. Go. Yep, so our first definition is going to be a definition of some odd numbers, which uses the exists. So that's right. I need to go to the next slide first. Here we go. And cover exists. Okay, so let's keep going with these operators. So this is the backwards E. It's exists. And in regular language, this is something is true if you have at least one instance of it being true. So a fun example is there exists an element with atomic number 43. So this is true. None of the others have the atomic number 43. And for years, actually, the periodic table had been proposed by Mendeleev, and people were like, hey, let's keep finding more elements in here. And for a long time, this was a gap. It jumped from 42 to 44. And that's because technetium is radioactive. So it doesn't exist out in nature. You have to make it inside of a lab by doing radioactive stuff, okay, to other kinds of elements. Nonetheless, it exists. And that makes this proposition true because there is that. And so the one example that is true, the vocab word for you is witness. That's the term for it. It's a witness. Like you can think, I saw that, like I am going to testify to the truth of that statement, and only one witness needs to, one witness is sufficient to prove this statement to be true. So there's two ways the existential can show up inside of a lean theorem. You can have it inside the hypotheses, and you can have it inside of the goal. So we're going to work through a few examples with this inside the goal. If it's inside of your hypothesis, you use the lean tactic obtain, and I will briefly pop over to the Mechanics of Proof textbook. We need chapter 2.5 just to show you what that looks like. So you can learn a lot more about existence type proofs, but the first one, I'm assuming there exists a rational number b. Okay, so that puts it on the front side of the colon. It's a hypothesis. Hypothesis, there exists a b. Okay, such that, that's the comma. The comma stands in for such that, essentially. This is true. And that's a mini little statement. So I'm assuming that's the case. Show that A must be greater than 0. This is going to be the thing I'm going to prove, my conjecture. And the obtain tactic is used. We're not going to dig into this, but you can totally go at Mechanics of Proof, work through this one, work through, I listed one more. 2.5.2 puts it on the hypothesis side of things. Today, we're going to be digging into if the goal has the existential statement. And this is Mechanics of Proof 2.5.3 and also 3.1. So I am jumping to 2.5.3 next. And show that there exists an integer such that 12n is equal to 84. Exists n as an integer such that 12 times n is equal to 84. The colon is on the left, so everything here is a goal, and it takes a short little proof here. I'm showing you this in the browser instead of in lean code because we've been doing lean code out of MathLib instead of out of the Mechanics of Proof. And something that Professor Macbeth did when she made the custom version of MathLib for her textbook was she made some tactics weaker, so things would show step by step a little bit more often. So I'm just showing you this one example because I think it's useful to stepping through the problem, but then we're going to go to lean with the MathLib tactics. And so here the goal is initially this existential statement. After we use 7, it replaces the n and the exist statement with a 7. So now we have this is the only thing we need to prove, and then she uses the numbers tactic. MathLib doesn't have the numbers tactic, Mechanics of Proof does. We use norm num for that, okay? But now you're able to close the goal. So that's what 7 is, the witness. That's the word here. 7 is going to say, there exists a natural number. 7 is a natural number, okay? And it satisfies this. I know that is true. I can't use a different number because if I use 5, it won't be true, but that's how it works, okay? All right, the next The thing we're going to get into in Lean, though, is from chapter 3.1, where we're going to talk about odd numbers. And the reason this one is interesting because the definition of odd itself involves existence. Okay, like we think of odd, I mean, how would I define odd? Well, it means I take my number, I divide it by 2, and I get a remainder. Okay. Um, or, well, yeah, but that's not a very convenient thing to use in theorem proving because the division operator is actually a bit more advanced. And this is simply a simple logical way to do it. You don't need division, you just need multiplication and the exists operator. And so this is a proposition saying there exists some number k such that a is equal to 2 times k plus 1. That's what makes the a an odd number. And so I'm going to hop over to VS Code. I need a minute to change my screen sharing settings. So I have great. Oh, we have a question. Why is K not defined as in Z? Good question. It is. Um, so lean is inferring the type of K here. If I put my cursor over K, you can see it actually does have type Z. Because, yeah, it doesn't work. Indeed, if I had, if A was -3, for example, I can't, there does not exist a natural number K. There does exist an integer K that would satisfy that. Yep. Okay. You'll notice a small thing that's different in the way I set this up, using my odd, because MATLAB has odd. So we would be overwriting the definition that MATLAB is using. If K is in R, then odd would not be properly defined, right? So we can't have K be a real number. It is not, though. It is just an integer. It couldn't be irrational either, but it's just an integer. We have a question here too.
Along the same line, what if you didn't want K? If that was
if my definition did want K to be a natural number, I could force it to have the natural number type. Good question. If we don't define anything, by default, lean takes Z, it does not. This is a good line of questions, actually. Let's explore this a little bit. If I write eval 1, okay, the type of 1 is guessed to be n. So the default tends to be the natural numbers. I didn't specify what the type n has. If I do eval 1.0, okay, now it says it's going to be a float type. I can't really write proofs with floats. We talked about that before. But it's also not a quotient, okay? in this case, it looked around at the stuff, the other things in the definition, and knows that A is an integer. And so, because it's also going to say 2 is an integer and 1 is an integer. It sort of guessed what types all of these should have. I wouldn't say guess, it inferred. It implicitly typed them, okay, in order to figure out what type. Because I did tell it A is Z. So then that bit of information said you're going to figure out what the rest of these types are. If I made AQ, look, it made KQ. It made 2 a rational number. Do we have a lean expert in the room? The question is, can I make a Q or Z? I don't think I can apply the OR operator to types. Can I? I've never thought of this before. Usually things have a type. I could call it alpha. We're getting into, I wasn't going to talk about types until next week. But there's also a generic type. I could name a generic type, and I can do stuff with generic types. And then depending on the circumstance it finds, it would then infer what it's going to be. We actually make use of that in certain things. But typically you pick the most expressive type that you need it to be. You name it as nat. As a natural, if it's going to be a natural, if you need to include negatives, you just forget about natural altogether and you just call it Z, for example. But that's a good question. Yeah, it is helpful to talk about where these type assignments happen and how that works. And Colin is making a really helpful point that 1/2 is neither odd nor even because there doesn't exist an integer k such that the definition of odd is going to satisfy, and there doesn't exist an integer k such that the definition of even is satisfied. So, and ooh, does it even need to be concrete? Could it be a ring? Maybe. You're talking abstract algebra stuff that most scientists and engineers don't follow. So, I'll leave it at that. The UI is doing these internal tooltips help. The UI is definitely where the cursor mouse over stuff comes from, operating through VS Code, but the lean interpreter is what is reading the lean code and giving it the assignment of what type it has. So it is something that is operating rigorously to tell you what is happening to each of these terms in this. Good set of questions. All right, did I get back to where I was? I did, okay. So, and I just changed my mind about this split screen because I have answers that I'm going to go back to this. Oh, maybe I can't even. Oh, yes, I can. All right. Okay. This will make me more comfortable. So we are going to prove. Okay, so this is a definition. The first word in the definition is going to be the name of this. That's how you invoke it. Then my type of my definition is a proposition. Okay, and my proposition is assigned. The colon equals, this is not like equality, which is a different thing. This is assignment. I'm assigning this property, this proposition, the following existential statement. Okay. That's how you sort of read and understand that. Now, how do I use this definition in an example statement? We've always sort of put the hypotheses and goal out here in front. We're going to say my goal, this proposition taking in A, so assigning the value of 7 to A, 7 being typed as an integer, I'm going to now prove that this proposition is true. And the first tactic we're going to be using is desimp my odd. I'm going to, let's see, so let's see this corner. There we go. The info view. Ooh, we have some more. Oops. Okay, so I want to close. There we go. I got my info view back. Okay, great. We are set. Another good question about the lean interpreter figuring things out. I think, yeah, before we move on, this is a good question from Manu. For those in person here. So then if the lean interpreter automatically assumes that K is in Z, then we can't really prove that K has to be in Z. And we need to use some contradictions that K can't be R and Q and R minus Q and so on. Okay.
What R is in the and then we can define it if we
Yes. So Jennifer here is saying, but we can define this. A definition doesn't hold you to anything. I'm not trying to prove that K has to be in Z. There's nothing about this has to that's really involved in this definition. I'm just saying this is what odd means. What you're probably trying to think of is you're trying to think of, I know what odd means. And odd has to mean this thing that's in my head. Okay, because I know what odd numbers are. And therefore, this definition has to be a certain thing in order for it to be semantically related to what odd numbers mean to me. Okay, we've talked about syntax, semantics. Okay, that's a gap between what something means to a person or connects to the outside world, okay, and how things are stated as lean code. Okay, so again, we didn't get any problems. We didn't get any problems at all when I said that K is a real number. Oh, come on. K colon R. There we go. I didn't get any problems. There's no flags. Like, if I wanted this to be my version of odd numbers, all right. I mean, I can go and prove other kinds of things about this. Like I will be able to prove that half is odd. I will be able to prove that 2 is odd. I will be able to prove also, no, I'll take that back. I will be able to prove that half is my odd. I could prove that 2 is my odd. Because my odd is just defined this way. K is a real number, right? It's not what I meant. It's not what you mean when you say odd, but it is just what the definition is. So back to the proof. Good questions. And yeah, we're at 1 hour, but really it is fine. We have time to get into these things. Okay. So desimp is a tactic that so we start with our proof and we have one goal. I need to prove odd 7. Put my cursor here. I have one goal. I need to prove that my odd is 7. So after I run the desimp tactic, which you can see desimp is the definitional simplifier. You can try to read the text. It is applying theorems that hold by reflexivity. Often you use this to replace a definition with the thing it is defined by. So it used to be my odd 7. Now we have my odd, the contents of my odd being applied to 7. So we have 7 exists k, 7 equals 2 times k plus 1. Our next thing is we are going to provide a witness. And to provide a witness, you say use. The use tactic provides a witness. And the text provides some illustrations and examples of how to use it. You can see after we've done this, we've replaced 3 and the exists front half of it with 3. Okay, and now I can close this goal because now I have a goal of the form 7 is equal to 2 times 3 plus 1. And we know that we can close those kinds of numerical things with norm num, and now we have no goals. So you might think, well, what if I use 2, right? What if I use 2? Well, now this step worked just fine. I have 7 is equal to 2 times 2 plus 1. And now I try to do norm num on this, and I get false. Okay, because, again, what am I trying to do with norm num? I'm looking at the state of this goal, and I'm saying 7 is equal to 2 times 2 plus 1. This is an equality statement that is not true. So I apply norm num, and it returns false. Okay. I can't prove false. I leave this example. I still have one proof I'm still out here trying to close. I didn't successfully prove this. It doesn't mean that the statement is false. It just means that my proof isn't good. You can write, there's an infinite number of ways for you to write a poor proof of something. But Lean will tell you when you've gotten it right or wrong. So that's how we get this. We can use the odd. So this is what I see if I put my mouse over on my odd, well, I see what it is I've defined it right here. It's a proposition. If I look at odd, this will say this is a proposition. We have a doc string. It describes as an element A of a semi-ring is odd. Semi-ring is an abstract algebra term. I think it's not something we explicitly cover because we can get around a lot of this Lean stuff without following these things. But if you're really going to get into Lean, you probably should figure out what all of those vocab words mean. Ring, semi-ring, field. It guides you on what kinds of tactics work when. But anyways, we're using the definition of odd from MathLib. So we apply odd here, and we can use the same proof here. I can unpack this with odd. Now I've unpacked it, and I can use 3 like before, and I can use norm num. That's all fine. With MathLib, we don't actually need the dsimp odd. Use 3 uses a smarter tactic, and it knows what odd is. It's a tactic that's been told about the definition of odd, so it can just jump right in and close it off right away. Norm num will do this. In fact, does it work with use 3? This one doesn't work. No, this one gets unsolved goals. It can't close it all the way. It leads you in the end. If you just use 3, it will say you have an unfinished goal, so you do need to hit it with norm num. I always found this to be annoying that you need to, in order to prove this statement, you need to figure out the answer yourself. In order to prove that 7 is odd, I need to find the magical number 3 that makes this, I need to find the witness. Well, MathLib does have cool tactics that don't require you to provide a witness. Decide is a cool tactic like that. So you can see I can just say odd 7 colon z, and I don't even need to provide the 3. Okay, but here's a little insight on what decide is doing. If I try to prove my odd 7 colon z, decide can't do that. Because what decide is doing is decide has access to a bunch of definitions and theorems and stuff in MathLib, and it's using those in order to solve these kinds of existential things. It doesn't know what my odd is, and so it's not quite smart enough to work its way through that, but it does know what odd is, so it can solve that. We'll see shortly how that gets practical. Okay. So we have a chemistry example. Huckel's rule. In cyclic molecules in a ring system, okay, the number of extra lines you see, if you don't know chemistry, okay, these are double bonds, and double bonds have pi electrons. Each double bond each has 2 pi electrons. So the number of pi electrons in a ring system is m, and n is some natural number. So Huckel rule says the number of electrons, so the number of pi electrons, I should have on the slide, must be able to satisfy 4m plus 2. That's sort of a natural language way of saying it, but like, what do you mean by you must be able to satisfy this? Okay. So we do our effort of formalizing this statement is there exists n such that m is equal to 4n plus 2. So this is a way to turn a rule from chemistry into an existential statement where what is n? I define this as whatever I need it to be, right? So that comes back to this conversation. Is n going to be z? Well, so I say n is some natural number, right? So if n is equal to 0, then we have 0 times 0 plus 2. We wouldn't be in this really exotic case where we do have an aromatic 2-electron system. When we were discussing this amongst the group, as we were trying to state this in the first place, I hadn't seen this little picture or considered this case. And so people were like, well, shouldn't we be saying, and there's a constraint that n is greater than 0? Okay, like if I'm not going to include this in my definition, this weird little highly unstable molecule, if I'm not going to include this in my definition of aromaticity, well, then maybe I should have, if this is not aromatic, well, now I need to have an extra thing, and n is greater or equal to 1, and n is greater than 0, something like that, would be another way to do that. But the 6 pi electrons case, n would be equal to 1, okay? This is 4 pi means we have an even number of electron pairs, so this doesn't hold, and so on. You could go and define non-aromatic as the alternative version of that, okay? So that's Huckel's rule for you. Let's go to lean code. I hope you enjoy this example. We looked a long time to find this, and I really like it. So here's some text description of that, and we have an example, and here's the solve proof. So we have m is defined as a natural number. We don't have negative electrons. We're counting number of electrons, right? Does that make sense? So we're going to call this a nat. Then I'm going to assume that m is equal to 6. We're going to do the benzene case. And this implies Huckel's rule. So if it's going to be true, then we satisfy Huckel's rule. If it fails to imply this, it would be false, and we would not satisfy Huckel's rule, okay? So exists n such that m equals 4n plus 2. So here's our statement in the lean thing. We have m is a natural, know that m is a natural number, and we have a hypothesis, m is equal to 6. So from this, can we prove that this existential statement in the goal state? And we use 1, and it closes out everything for us. So we have no goals after this. And I put for some reason, because I don't quite understand this, use here is also performing numerical simplification and closing the goal. It's not simply replacing in the goal state. It's not simply going to the goal state and returning m is equal to 4 times 1 plus 2. A way I sort of figured this out is if you make it a little trickier, then it uses 1, and we do replace the n, and so our goal state is now 4 times 1 plus 2, and we have a hypothesis. It wasn't able to automatically figure out that m is equal to 6 and close it out automatically. So use is doing a little bit of, in the previous version of this, like use is doing some simplification. I would be able to close this by showing that with h1, I can prove this to be true with some other things. But that's a little implementation detail that might be curious here. Okay. All right, and now this is a cooler way to define Huckel's rule. Let's see the whole explanation. Okay, we're just going to count electron pairs. You know, the number of lines. Electrons are often paired like this. Okay, so the molecule is aromatic if it has an odd number of electron pairs. That's pretty straightforward. If it has an odd number of electron pairs. So what does that mean? Now I'm going to say there exists some n such that here's an AND operation. M is now the number of electron pairs and odd n. Isn't that nice? It's pretty fun. I like this. So this one is a little harder to prove, but I'm going to ask. We have plenty of time. So we're going to see. I want you to think with me, how should I close this goal? What tactics should I use that we've been introducing so far? Between this lecture and the previous ones, you have all of the tactics that you need. So DSIM, okay. Well, let's first take a look at this. Yeah, so we have odd n. Okay, so we could potentially use DSIMP to replace odd n with the definition of that. Can I? Let's try it. DSIMP odd. Okay, it worked. Arshak is saying constructor. Can we use constructor? What does constructor do? It splits out AND statements. So we would get 2 goals. Let's try constructor. Uh-oh. Constructor did something funky. Ooh, is the DSIMP ahead of it? Does that matter before constructor? I don't know. Well, let's try. I mean, I do know, but we'll show it. Here we go. Let's do constructor first. Put the cursor after constructor. We still have the same problem. Okay. Question W, okay, it has a type. Question W has a type, it's type nat. Okay, but this is a synthetic whole. Okay, it's used to construct named meta variables. It's kind of weird. Okay, we're not, you need to know a bit more about lean in order to know what those error messages mean. Okay, but bottom line is not in the right direction. Colin is saying we have to provide a witness first. Okay. The existential applies to the and. We have to be careful. Let me move up to here because the existential n is showing up on both sides of this. If I split the and into 2 things, I wouldn't be guaranteeing that exactly the same n is part of both of them. It's kind of tricky. You know, maybe I could use 1 to prove the first one and 3 to prove the second one. That does not allow me to prove both of them. I actually need to resolve the exist statement first. So we need to provide the witness first. We are going to use 1. And I will use 1. Okay, now we are on the right track. And we've simply replaced the and statement with 1 in place of both ends. Now what should we do? The thingies above. Norm num, we can try norm num. Norm num. So norm num leaves us with m is equal to 2. Oh, why am I using, should I be using 3? Use 3. Okay. Now we have, well, after running norm num, I think you're right though. Also, we should use the right thing because we won't be able to get to m is equal to 6 with 2 times 1. Yep. Okay, so we're using 3. Norm num doesn't close the goals. It does rewrite the odd as not even. Okay. But it doesn't, and it does simplify the 2 times 3. Okay. But yes, now Arshak Gonzalo are saying we have constructor. Okay. So I'm going to do constructor first. Constructor is going to break this out. Now we have 2 separate goals. So we can now, how do we prove the first goal? Well, the first goal simplifies the, I'll take away norm num. Okay. So now we need to address the first goal. How do we prove that m is equal to 2 times 3? H1. We are assuming H1, so we will use that. We'll use the rewrite, which is substitution. Okay, it's gone. Only 1 goal left. How do we prove odd 3? All right, we can use dsimp to open it up. Dsimp odd. Okay. Now we have another existential statement. Use 1. Looking good. Almost there. 3 is equal to 2 times 1 plus 1. Norm num. That's right. Do our little thing. We got no goals. We did it. All right. So a couple notes here. We don't need dsimp odd when we're working with overall mathlib. Okay, we don't need to unpack odd. We can just use 1 and it will work all of there in one shot. We can also, we don't need to provide a witness for odd numbers because we have the decide tactic. Decide will close it off for us, make it easier, make our lives easier. And that's, here, I'll leave the one everybody wrote together up here. I put a copy of this here so I could show a more efficient way to do this. We still have to use 3 and rewrite H1. But now decide actually works just straight away. Decide can handle the dsimp, the use 1, and the simplification all in one for this case, and the constructor. We didn't even need to do constructor because there's an and statement and other things like that. So the rewrite is just going to replace m with 6. We do need to get a number in there. M is a variable. Now we're left with just numbers. And the logical operator and dsimp and decide tactic is able to handle that along with the odd. So everything here is about natural numbers. This is a shorter, more compact way to handle it. But you still need to use the 3. Ooh, actually, let me see. I'm curious. So if we hit it with rewrite H1 first, Now we only have numbers, but decide can't handle this one. So this one ends up being too complicated for it. Again, for the reasons we're defining our own thing. M is equal to 2 times n. That is a separate definition that decide doesn't know about. It's a little bit more complicated. Yeah, someone's trying, what if we did decide before rewrite? Well, this decide doesn't know what to do with it either. Now we have a variable in there, and it's even worse. Okay. It's not making progress on the goal. Yep. So I'll go back to the tight one. This is the tight solution, I would say, that at least that we found. Okay. So coming back to this idea of definitions, we can create a definition for the concept of aromaticity. Isn't that nice? Now this exists out there in the code. It's not part of an individual example. And so I have two versions of this. The first one is the 4 times n plus 2 that we talked about. The second one is the 2n and odd n, so we could have either one of these. These are both just propositions. And I mean, it matters what we define these as. M is a natural number, okay? So it's not a rational number. We don't have a rational number of electrons. We have a natural number. And with this, with these definitions, we can create a more generic setup. So now I'm going to say, does benzene ring electrons being 6, does 6 have the property of aromatic? It does. Yep, it does. Well, this will be the same example that we just did. 6 satisfies this. We did that one right here. So 6. So the answer is yes, it does. But we're stating this question: does benzene have the property aromatic? We've done something semantically here, and we've defined the meaning of the aromatic property. We can then go and prove these things. We do need, can I use 3 here straight up? Yes, I can. I don't need to use dsimp right off the bat. So I can use 3. You can if you want. So like I can do dsimp aromatic 2. And go and say, you know what aromatic 2 is, you go and find the definition, replace it in the goal here. I can do that. I can also just cut to the chase and follow this exact proof. I'll just copy it. Oh. Close the goals. Okay, the same thing works. This is mathematically the same setup, but the point I'm bringing out is we have a definition here. Definitions are cool because I could write this. Find the time. Okay. I could pick a different molecule. And I'm not restating my definition of aromatic. My definition of aromatic is exactly the same. Okay. I could try, I mean, what I'm naming this doesn't mean anything. Okay, I could give this benzene M is equal to 8. Okay, like I haven't, it's still named benzene. It's not telling me there's a problem here. We would have to do extra stuff to actually connect this to some representation of a benzene molecule in lean. But I could just say, I don't know, M is equal to 8. So we're trying to do this. Does 8 have the property aromatic 2? Okay, I'm failing to prove this. I could state this as not, for example, and then get a positive proof of that. Okay, just failing to prove this doesn't prove that this is false. It only says my proof isn't good enough. In this case, I would try forever and I would never find a good proof for it. In general, if you're struggling with that, like if you're trying really hard to prove something and you're not able to do it, well, double check and make sure you're trying to prove something that's true. Because you can only prove things that are true. If I switch this to a not, then I'm not going to go into that thing because I didn't prepare examples for that. You can learn about doing proof by contradiction in mechanics of proof. It's a bit more advanced and involves some extra ways of thinking logically about these things, but I'll leave this one here. But that's the general idea of like what it means to have a definition. You can reuse that definition. If I would just be copying and pasting this existential statement in here, if I changed it in one of these, it wouldn't carry over to the other one. That's what modular code does. You know, we've made the definition of arithmeticity modular, so now I can use it 100 times elsewhere in my code, and they all refer to the same idea of arithmeticity. Yes.
But does it always have to be used through? Like, isn't that very limited? Like, if there's a witness, is it just but is that all we're trying to do? It seems like it wouldn't.
Very good question. It feels like use 3 is very limited. You always have to do that. If you are proving something with a witness, you need to provide a witness that's correct. Okay. There are some statements which might have more than one witness, right? Like if I maybe any negative number will suffice to prove my statement. So I just need to use -1 will work, use -5 will work, use -99. You know, that will potentially lead me on a path to doing it, but I do need to provide it, and that's annoying. Mechanics of proof always has examples with use. And so that's when exists is in the goal statement. All of the examples in mechanics of proof involve a witness. And I asked the people on Zulip, how would I do this without? And that's where they told me about the decide tactic. So the decide tactic, it is actually doing the proof with a witness, but it's finding the witness for you. It's doing a bit of a search. It's doing a bit of a logical thing to track down that witness. If that's not completely true, someone who really knows how this tactic works, maybe correct me. But as far as I understand, it's doing a search for a witness. That's why it fails here. It was unable to, well, in this case, it couldn't synthesize it because it couldn't resolve it. But there are some tactics which will time out. They will try searching for a thing. They might try 100 times and then they give up. And you can increase the amount of times that they try by changing a setting, and they'll try harder and then give up. That's something that happens in Lean. It's a very good question. Yep. Okay, so for all is next. Last chance to ask about exists. Okay. For all, something is true if every possible instance of it is true. So let's look at the transition metals. All transition metals have unfilled d orbitals. A lot of them do, okay? But zinc is a transition metal with a filled 3d orbital, so it's false. So the for all statement is going to be false. It only takes one example to falsify. It could take more, you know, but you need to have every single value satisfied. From a software verification perspective, I think for alls are really, really powerful. Because if you can prove a for all statement, you know you've covered every possible edge case. And that's really, really cool. The I should bring this back. Okay, I will go and pull out a slide from lecture 1 to elaborate. Are existence proof more meaningful when we're looking to find a unique witness in the domain? I'm not sure. Mechanics of proof does, let me go. Proofs with structure 2 has 4.3, there exists a unique. So I'm not covering any of that here. Dig into mechanics of proof 4.3 and learn about how that is set up. We can look at the statement, okay? That exists explanation point is the lean syntax to say there exists a unique. Use 2. So I'm going to say 2 is the unique witness to this, and now I go and prove this, okay, and close it all off. We have a half an hour. We have time. Let's work it. Let's work this one in lean so we can see it. Good question. Thanks for asking, Simon. We don't use numbers. We use norm num. All right. No goals to solve. We're set. Okay. So explanation point means there exists a unique x such that px, okay, by use 2. Simp to clean things up. Okay. Now we have 3 times 2 plus 1 is equal to 7. And for all. Because in order to prove there's a unique and exists, we need to prove something about everything in the domain. Okay, so I guess I should finish talking about for all first, but this is just, we'll go through this one quickly. We want to say that for all values of y, this is also then going to be true. So that is what happens when I apply, when I unpack a unique exists, we get exists and for all statement. We have an and statement, so we split it up. We prove the first one. So this center dot is how you tell it I'm going to be working on this at all. That is, you write that with /c dot. Don't do that. Did I do that right? Let me make sure that is the right shortcut. Cursor over this is, oh no, you just do center dot. You do center dot, excuse me. Yep, explanation point does mean there exists unique. Yep, that's what we're jumping on to Simon's question here. And now we have, after closing off the first goal, we have a for all proof statement. This uses intro, we'll get to that in a second, but we use then for all tactics. This one also has the implication. So technically, yeah, that's a good point. This is, we weren't going to cover that, but yeah, this is more stuff in chapter 4 that you can dig into, and good question. All right, so I was talking about for all, and oh yes, so I had a proof from lecture 1, a little example. Here it is. Okay, this one uses a for all statement. So if you recall, we were talking about harmonic motion. We have a force on a spring. We define a couple functions, and we define the derivative of this function. And if you were going to write a test in Python, you might check whether 5 gives you the right answer for force. But in Lean, you can be more fancy. You can define a function. You can use these functions to calculate things. And then theorem is going to be force is derivative of energy. And this upside down A is the for all symbol. For all values of x, this holds. So I'm going to be guaranteeing this property for every single thing that's a real number. I've caught every edge case. Does this hold at 0? Does this hold at pi? Does this hold at -1? Okay, I've checked all of those simultaneously with my theorem. So that's why for all is a neat thing to bring in into these proofs, because when we're trying to do verification of software, so we're presently working on implementing molecular dynamic simulation code in Lean, and we wanted to prove something about the Lennard-Jones function, and it was like, we can't actually prove this because it isn't true when distance is equal to 0. And Lean told us, like, you're not actually going to prove this for all values of x because it doesn't hold at x is equal to 0. And we're like, well, okay, got it. It's not like I encountered distances of 0 in a practical molecular dynamics simulation, but it's telling me when the math doesn't hold. And that's why I think this is particularly useful and curious. It only takes one example to falsify a for all statement. That's how powerful it is. So first we're going to look at example 4.1.1, and then we're going to look at a chemistry example, a physics example. All right. And that is why there exists a unique comes after for all, because it does involve combining exists with for all. Okay. So example 4.1.1. Let a be a real number, and suppose that for all real numbers x, it's true that a is less than or equal to x squared minus 2x. So here's the parabola, x squared minus 2x. And -1 is always going to be greater or equal to a. A is always greater or equal to -1 when a is a real number. It's always less than. So, oh, I missed a vocab word. Existentially quantified is what existence does. Universally quantified is what the for all object does. Okay, we're not going to keep using that since it's a little bit mathy, but if you come across that language, existential quantification, universal quantification, that's referring to existence and for all. And so we use the upside down A. And this is a hypothesis with a universal quantifier. So I'm assuming that this is true in all cases. I'm not proving that this is true in all cases. It's not in the goal state, it's in the assumption state. So I'm assuming this is true in all cases. I'm not proving it's true in all cases. This is a little bit different. And so the strategy to write these kinds of proofs when it's in the assumption is to specialize its use to one particular variable. Or this is one strategy. And I may want to say, set the case of x to 1 in order to show that this is the case. And so we can use this with apply, and we have an example here. I popped this out in Lean. Oh, I forgot. We actually came up with a cleaner example. Yeah, okay. Well, so that little bit more complicated example is down here. Excuse me, I forgot to talk about this one first. This is a different one. It says, for all, okay, so here we have colon, we have a for all in the goal statement. So this one is a little different from the other one where for all is in the premises statement. Okay, and so if for all is in the goal statement, I want to just prove for all x as real numbers, x squared is greater or equal to 0. So no assumptions are on the left side of this. I'm just saying this is simply true about math. no matter what, like, and so we now have the for all x as real numbers, x squared is greater or equal to 0. The tactic to address for all statements is to introduce one or more hypotheses, and you can optionally name them. So intro x is going to, I could do intro hx. I could call these different things. It's probably a little bit cleaner to state hx, or intro, I don't know, z, we can pick what we want. So I perform intro z, and what it does is it changes my goal state to z squared is greater than or equal to 0, and it puts something into my assumption state. I'm now assuming that z is some real number. I'll state that again. I think it takes a little bit to track this, okay? I was trying to prove that for all real numbers, x squared is greater than 0. For all real numbers, x squared. After I apply this tactic, I've simply moved x into my assumption as a real number. So I'm assuming x is a real number, and if this is going to be true, it has to be true for all real numbers, because x is any real number. That's essentially what I did. I substituted z for x, but I also moved z into the assumptions. Yep, that's sort of, you know, the tactic intro. I'm introducing a new assumption. I'm introducing one or more hypotheses. Hypothesis means assumption in math language, okay? And it optionally gives them a name. It optionally, how do I intro z as HB? No, maybe I don't do this. Anyways, this one works. And next, so we talked last time about how you use math theorems. So we are now going to go to MathLib and prove that the square non-negative theorem, which is in the MathLib database, that states that 0 is less than or equal to a squared. Someone went and proved this already, so we don't have to do it ourselves. We can say exactly this theorem with z when this theorem, so this theorem you can see, oh, I lost it, is about any variable a, any real number a. So if I say pass in z into this, we will get this, okay? Ooh, I'm gonna do a clever little thing. Let's make this a complex number. Am I allowed to do this? Oh, it failed to synthesize. Okay, because power doesn't quite work. Never mind, forget that exercise. But this wouldn't hold for x being a complex number, because complex numbers squared might be negative. And if z had type complex number, this wouldn't hold anymore. So we wouldn't be able to use that theorem. And that's another way that Lean checks and keeps track of things. A quick reminder, since I think we're still okay on time, let's go to the Lean documentation. MathLib documentation. You can find that here, and you could search for square non-negative. Okay, you know, like if you were trying to think again, like, so try to think of what it might be called. This is what that theorem is named as, and a whole bunch of stuff in the preamble, but it is going to prove that 0 is less than or equal to a squared, and that's what we used in order to prove that. And these are all the weird math conditions. I think I mentioned this before, but MathLib, since I was talking about abstract algebra before, a reason it can be useful to learn some abstract algebra and learn what some of these vocab words mean is because MATLib isn't going to include 0 is less than or equal to a squared when a is a real number. That's not helpful for it to include in, it's not the best version of this statement because there are more generic forms of this that would say, there are other types than a being than real numbers where this would hold. And so that also holds for naturals. It also holds for integers. It also holds for semi-rings. And essentially, the way MATLib is built is the most generic form of the theorem is in MATLib. It's set up so that if you pass it a more specific kind of thing into it, it can still prove it. Because you can prove a specific case from a general thing. And if you don't know where this came from, that's okay. It will feel like that for a while as you learn how to navigate the documentation, navigate the different search tools that are out there. But the reason I wanted to pull this out was just because I'm curious as we're talking about this. We can go to the source. We can see the theorem statement. How did they do this? They did obtain. So this involved a, obtain tactic. You learn about that if your existential is on the assumption side. And we have a whole bunch of other math theorems, and even a calc block and rewrites and simplifications and so forth, and it's all proved that way. So you can go and find evidence of this theorem being true for yourself. We could go and write this ourselves, but we don't have to because we have something in MATLib for us to do that itself. Okay. So that's a case illustrating. We use intro to unpack that. When it's on the goal side, we use intro to move the thing that is true all the time into the assumption, because if I'm assuming it has to hold for all of those cases. Now we move on to that parabola problem that we had in mechanics of proof 4.1. And here we have a is less than or equal to this. So I start with an assumption state for all x is real numbers. A is less than or equal to this. So I'm assuming that this is going to be true. How can I use this information, which I know to be true, in order to prove something like this? We can, for example, jump into a calc block that takes the form of this statement and say, I know that this statement is true because h is true for all values of x. If it's going to be true for all real numbers x is being replaced in here for 1. Well, if it's true for all values of x, I know it's true for 1. So I know that this statement is true. Make sense? I'm getting nods, okay? Then I know the right-hand side of this inequality statement. I can go and prove that 1 squared minus 2 times 1 is equal to -1. I can prove that statement with norm num, and now I've proven a is less than or equal to -1. So that is an illustration of way to use apply tactic when the existential is on the assumption side. We can use intro tactic when it's on the goal side. And finally, we have one more, which is an implication kind of proof. So we talked about implication a little bit, and we're using the implication operator, and we're going to prove a curious little example from Newton's equations of motion. If we're just looking at Newton's second law, when the net force is 0, that implies acceleration is 0. So assume F is equal to mass times acceleration. We're also assuming mass is positive because that's how physics tends to work. If I'm assuming these two things, can I conclude that the following statement is correct? F being 0 implies A is equal to 0. So how do we do this? Well, I didn't give you any tactics for implication type problems, but intros, I can intro if I apply intros on this goal state, does intro do anything? Intro does exactly the same thing. Okay. We used intro with the for all statement to move x into the assumption here. We're using intro on this implication statement to move the left side of the implication into the assumptions. So you think of a proposition, A implies B, P implies Q, okay. I can change, if my goal is to do that, I can do intro and I can just say, well, I'm assuming A. Now, something is easier, okay. I only need to prove Q. It puts this little A dagger here. That's kind of weird. I have a hypothesis. F equals 0 is a proposition. It needs to have a name. I need to have some way to access it. It's kind of weird. Lean is going to be like, well, I have a name for it. It's a unique name. Okay. It's in the assumption, but it's cleaner and easier if we give it a name ourselves. And so you can give it a name. H force now has a name. I've given it a name. We're good to go. All right. So now should be able to do this. Okay, this is an inequality. We covered inequalities in lecture 2. So, any ideas? We have 8 minutes. This is the last thing we're doing. So, can't use exact. So exact is going to, we need to have exact either as a theorem in MathLib directly, or we need to have it exactly stated in one of the hypotheses. We have a suggestion. Oh, I will, for the people in person, I'll move the chat over to here. So we can see it all. Nope. Okay, we're still good. Optimizing the window. Okay, norm num bracket H force. Let's try it. Norm num bracket H force. No, it did not. What? Why am I getting intro and failed? Well, it didn't like this. H force, comma, H1. We don't need H2 at all? See the trouble? Okay, so think about it. Do we need H2 at all? Well, the problem is if m is equal to 0, if m is equal to 0, this does not hold. Yep. if m is equal to 0, I mean, unless someone can give me, oh wait, did I have an extra space here? There we go. Okay, yeah, but still, we still have unsolved goals. Okay, if m is exactly equal to 0, well then I could have force be equal to 0 and A be equal to 5. Yep, so it would not hold anymore. This proposition would not hold. And so we need to have M. We need to have H2. Yeah, we don't use construct because we don't have an and yet. Okay, I can't do it. So norm num is not able to do it locally here. I have a strategy here. Let's try to use what we have. F is equal to 0 and prove that m times a is equal to 0. Let's do that. So there are a couple ways we could do this. One way is I could introduce a have statement. So have is how we do intermediate steps. Have, let's call this force 0. I could say m times a is equal to 0. I just believe this to be true, okay? But now I need to have evidence for this. I will go and get H force and H1, and I'm going to rewrite that. So I'm going to do I'm going to do substitution with, I'm partly going off the answer key, which I know works, but this is a clean way to do it. I could just do H force, comma, H1. Did I do that? Did I spell H force right? I could just use ring. Oh, totally. Oh, does ring do everything? Or you're just talking about the last step? By ring? No, ring doesn't do this. Does ring do everything? Okay, yeah, just for the last step. Not quite. Ring NF, they often suggest that if ring doesn't work. Nope. Okay, let me try putting MA time MA equals 0. M times A. I have a solution. I'm gonna work from that one since we're running low on time. Okay, this one works by substitution of we're going to use left arrow H1 and H force. So we're doing a substitution with F is equal to 0, and we're substituting that into we're replacing the left side of H1 with this. We don't need the left arrow if we're replacing something on the right-hand side. We need the left arrow if we're replacing something on the left-hand side. Okay, so now we have a new statement that is going to be helpful for us to prove this. And we proved that it is sound. We can add this safely to our set of hypotheses. It doesn't create a contradiction because we have a proof that it's okay. So there is here, I'll just keep moving. Okay. We're running low on time. This is the solution that my student Kevin Ishimwe came up with. I'll just get it all out here and then exact F0. Okay. No goals. Great. So this uses the less than not equal theorem from MATLAB. Knowing that x is less than y, I know that x is not equal to y. And I know that y is not equal to x. So I apply this theorem at f0, and I'm able to go from m times a equals 0 to a is equal to 0, because I know that m is greater than 0. Do you find this with simp question? Kevin, is Kevin online? I wonder if that's how he found it. Simp question. No, made no progress. Okay. So he found it by knowing about MATLAB. Simp H2. Would a simple calc work? We could totally do a simple calc. Let's try that. Let's try that. So that's the version that I had in my answer sheet. Let's try a calc block. So I need to prove that a is equal to 0. So let's say a is equal to, I mean, I don't know. It's a little tricky because we're not trying to do a calculation. We will need to invoke at some point a theorem that m being greater than 0, along with m times a equals 0, requires a to be 0. And we're at 3 o'clock, so yeah, I don't think a simple calc block is going to work, because you'll usually start a calc block with a is equal to something and then show that that something is equal to 0. And we do calculation, we do inequalities, but this one's a little bit trickier. Ooh, a is equal to force divided by mass. Yes. I mean, and this might be a path forward, because in order to do this for real numbers, we will have to lean on m not being equal to 0. So if you're thinking of it just being algebra, okay, it's not that. It's not quite, because you're not actually allowed to do a is equal to force divided by mass for real numbers when mass is equal to 0. And that is the case we're trying to avoid. So that might be another way to do it. Here's what. We're at time. So I'm going to wrap up the recording now, but definitely get onto Zulip. If you find other solutions for this, share them on Zulip. You'll get this whole, like as usual, you'll get the post-lecture set of lean code on Zulip as well. And then, yeah, if other people find a easier to understand way to prove this that I might use next year in this time of the lecture, then that would be welcome, and be happy to do this, because we haven't actually talked about what simp does either. This is one of the simplification tactics. This is also probably could break this up into a couple different steps. And yeah, but if we know m is not 0, then a must be 0. We know that m is not 0 because of other things. Yeah, homework. Okay, so homework. Good question. So as usual, we don't quite have the bandwidth to develop a bunch of independent homework problems for y'all, but mechanics of proof, chapter 4, basically, is where we're at with this. You can go and do a whole bunch of, so I'll scroll up to, we have, if you want to do more stuff with odds and evens, that's in chapter 3. Existence proof. So we basically did do 2.1 to 2.4 yesterday. Today we did existence proofs 2.5. We played around a bit with, so parity is even odd. Divisibility is fun. We didn't touch on that at all, but if you want to look, you can. And then proofs with structure for all and implication involve the intros, tactic, moving things. You know, do you introduce a new hypothesis in different circumstances? And I mean, that's what I would say, mainly 4.1. But if you're motivated, there's all these other exercises that you can do in these other things to build your skills, learn about other things. There exists a unique element with, you know, with atomic number 43. You know, that might be a fun one to actually do. But you would need to formalize what is the concept of an element and these properties, which we haven't done yet. But yeah, that would be my assignment for the future. Next time, so again, you don't need to do chapter 5 unless you are inclined to and you want to. We are skipping induction and number theory. You need those for understanding the mathematics of this a bit, and proofs by induction are really clever. They allow you to prove things like there's an infinite number of primes, which is a really satisfying and fun thing to do. But we're skipping these so we can stay focused on the stuff that's more directly associated with math and science and formal proofs about programs. So we're jumping to functions next, and that will be next week. Thank you.